Hi everyone. Today we have a little bit unfinished discussion about the linear time sorting, and then we will move on and start a new chapter talking about the median and the other statistics. Okay, so let's do a very quick review of what we have covered in the last lecture. We started from the comparison source, and we say so far we talk about the bubble sort, insertion sort, and then the heap sort and quick sort and merge sort. So for those algorithms we have covered in our lectures, and so far they are all comparison sorts. And for comparison sorts, we are doing pairwise comparisons. And eventually, after we have done enough pairwise comparisons, we will provide a solution of a final sorted list. Well, it doesn't matter what is the strategy of doing the pairwise sorting, or how do we design the iteration or the recursions to do the comparisons. We are doing comparisons anyhow, and as long as we are doing pairwise comparisons, and then we can create a tree structure, and from the very beginning to the very end, very beginning, and we started to do one comparison, and then depending on its greater or smaller than, or greater or smaller than, or greater than or smaller than, and then we want to move on, and then we do another comparison. We do one comparison, move down, another comparison, and eventually what are the leaves? And the leaves will be the final sorted version of the list, right? So this is a tree structure for a comparison source. And then, well, we need to understand that if we have n values, and then the final product, the final sorted version of the list could be any possible shuffles of those values. So there has to be at least n factorial number of the leaves. So well, the height of the tree will be O n log n. And if the height of the tree is O n log n, and this means, well, from the very beginning we started to do one comparison, and then go down to the last comparison, and there are O n log n comparisons to do. And this means, well, O n log n is the n log n will be the lower bound possible for this kind of comparison based algorithms. And then we move on and we talk about the counting sort. And for the counting sort, and remember, we are breaking one of the rules. The rules is and the rule we are breaking is we are no longer doing any comparisons. But instead, we have to put a higher or stronger assumption there. We are assuming that for all the values we are sorting, they are in the range from 1 to k, and they are all integer numbers. Okay, so here we introduce another parameter, which is k, and then we know there are a total of n values. And then, well, since we are now doing comparisons, and then the running time will be O n plus k. And if we assume that n is going to be much greater than k, or we say k is O(n) as well, and then we can consider this as a linear time algorithm, which is O(n). Well, and plus, this counting sort is a stable sorting algorithm, and we love that. And what are the problems? The problems is not really a in-place sorting algorithm. We are building two additional arrays on the fly of doing the counting sort. We are doing the B, and which is the output. And on the fly, we are also doing another list C. And what do we call that list C? Do you guys still remember? That is dispatching table, right? So this is the name given by me because we are building the C as a dispatching table, and eventually on the very last round, so on the very last round of the counting sort, and then we are grabbing the values from the A, and then for each of the A value we grab using the information from the C, the dispatching table, we can dispatch that value from the A, and then we move it down to B, and this is how we do the dispatching, and we are building a B, which is the sorted values to return. Okay, and then we move on and talk about the radix sort. And for the radix sort, we are sorting a list of the values, and then we have one more parameter D. What is the D? So the D says how many digits are there on all of the numbers to be sorted. This is again a very strong assumption because if you see this example, we are sorting integer values and all the integer values are 3 digits, right? So in this case, D will be a 3. Okay, and then how do we do the sorting? We want to sort all the digits from the least significant up to the most significant. And then for each of the paths, we are only sorting 1 digit. And remember, we have to use a stable sorting algorithm in this case. So if you want to see this example, and this is the unsorted list, and then the first pass, we want to sort all the values, all the values on the first digit. Okay, and then from 0 to 9, okay, we only do the first digit. And the second pass, we do the middle digit. And then on the last pass, we do the last digit. So we are sorting from the least significant digit up to the most significant digit. Okay, and then we also have to discuss about the correctness of the radix sort. And say in the middle of the radix sort, and there are two cases. Say if we say we are in this step. So for this step, in our plan should be, well, we know the first digit, the least significant digit, has already been sorted. And then if we have the same digit on the same value on the middle digit, say 2, 0, and 2, 9. And then, well, if those 2's are the same, and then we are going to use a stable sorting algorithm. So, well, this 2 and this 2, even those 2's are the same. But if we are keeping the order from the from the earlier pass of the sorting, and then we don't have to worry about getting it wrong because 2, 0 is here and then 2, 9 is here because the first digit has already been sorted, and then we are doing a stable sorting. So we will have 2, 0 first and then 2, 9 the second. So we won't mess up with things. And if we have if we have one specific digit and then two numbers are different, say if we are comparing the 2, 9 with 3, 6, 2 is smaller, so 2, 9 is going to be put first before the 3, 6. So in this case, it doesn't matter for this digit we are comparing with two same numbers or two different numbers, and then we are making use of the stable sort. Even though we are only sorting one digit at one time, we won't mess up with the rest of the digits that have been sorted already. Okay, so this is the trick of the radix sort. And let's move on and talk about the bucket sort. And for the bucket sort, again, we have a very strong assumption. The assumption is, well, we are assuming that all the input values n are real numbers from 0 to 1. So 0 is a square bracket, so that's included. And then for the 1, it is a parenthesis, so it's excluded. Okay, and then our strategy will be, we want to create n linked lists, and for each linked list, and we call that a bucket, and the size of the bucket will be 1 divided by n. So depending on how many buckets do you have. And one of the easy things we can do is we say, if we assume that the number of the bucket is 10, and then, well, from 0 to 0.1, that is a bucket 1. And then to 0.1 to 0.2, that is a bucket 2. So we have a total of 10 buckets. And then when we have a value to be sorted, we want to first decide which bucket to put that value into. And then if we have already decided which bucket this value falls in, and then inside a specific bucket, for example, from 0.1 to 0.2, that's a bucket. And then inside this bucket, all the values will be sorted using a insertion sort. Okay, and let me show you an example. Say those are the values I want to sort, and then I'm creating a total of 10 buckets. So, well, the first bucket is from 0 to 0.1, and then the second bucket is from 0.1 to 0.2. As you can see, well, from 0.1 to 0.2 we have 0.17, and we also have 0.12. Okay, for those two values, they are in the same bucket, but inside of each bucket there will be a linked list, and all the values are sorted from low to high. Okay, and then after we have put all those values into those buckets, and what do we do next? We simply try to start from the first linked list, and then we grab all the values from low to high, and then we move on to the second bucket. We grab all the values from low to high, and then we just put them all together, and then we will have a sorted linked list. And then you will find that well, for putting the values into the list, or we want to retrieve all the values and grab all the values from each of the buckets, put them together, they're all linear. So we have a O1 multiplied by the bucket size, or the number of the buckets, so we have an ON. And this idea, we are gonna come and talk about this idea a little bit more when we study the hash table. Okay, so this is the bucket sort. And again, let me ask you this question. Well, probably this you find that when we talk about the linear time sorting algorithms, I ask this question again and again and again. So let me ask this question about the bucket sort. Why don't we use bucket sort more often? So think about that. Okay, so well, number one, again, as we have discussed about the counting sort or the radix sort, well, we wouldn't say bucket sort is really a general purpose algorithm. And remember the range of the range of the values, well, we have a very strong assumption there. And what else? Well, we are assuming that we have a uniform input distribution. And in reality, probably we don't know the distribution of those values before we sort them, right? So in this case, and if we just create a range from 0 to 1, and then we find that all the values are squeezed in one single bucket, that is not the best case for the bucket sort anyhow. So well, for almost all the linear time sorting algorithms, this is a problem. We have to put on a very strong assumption, and in most of the cases, we don't really know this assumption is really true or not if we just throw in a random list of the values. Okay, so this is about the bucket sort, and then and this is the end of our discussion about the linear time sorting algorithms, and we have talked about the counting sort, the radix sort, and then the bucket sort. And those algorithms are cool, and those algorithms are smart. But among all the sorting algorithm we have talked about, and if you ask me to identify one of the winner, one of the sorting algorithm I would love to use every day, that's still the quicksort. Okay, even for the quicksort, it is n log n, but it is among the best n log n algorithms. Well, and for the worst case, the quicksort, it is O n square, but we can plug in a little bit more craftiness to avoid the worst case from happening. Okay, so that's it for the linear time sorting algorithms, and in the next video we are going to start a new topic. So see you later.